Okay, so let's start. So we are very happy to have Professor Artur Sergyeyev from Silesian University in Opava. He will talk about infinitely many new 3+1 dimensional integral systems from contact geometry. So please start.
Okay, well, good afternoon, I guess. Konnichiwa. First of all, it's my great pleasure to thank Professor Masashi Hamanaka for the kind invitation to deliver this talk at his seminar. Okay, so as you see, I am going to talk about integrable systems in 4 independent variables. And let me perhaps start with a bit of a general introduction to the subject of integrability. Well, with apologies to the experts, I was told that some people in the audience would appreciate a bit of, so to say, a general panorama of integrable systems. So, as I said, I hope the experts will indulge me when I go on with this brief reminder. Okay, at the very general level, if we are looking at a system of ordinary or partial differential equations, it's quite often helpful if we have at our disposal exact formulae for at least some of its solutions. Okay, and this, of course, has quite a number of useful applications. So if we have exact solutions at our disposal for one, or at the very least, one could use them as benchmarks for testing numerical methods for the system under study. But okay, and there are, of course, many other applications, especially for systems that are relevant for physics. Okay, and of course, it's nice if we are lucky enough, if our system can be solved exactly in some reasonable sense. Okay, and the question is how we do formalize that and what we can expect. So, okay, again, proceeding with a reminder, for ODEs or systems of ODEs, we have a quite nice and clear notion of integrability by quadratures. Okay, we say that our system is integrable by quadratures if its general solution can be written using quadratures. And well, here's the standard example. So one-dimensional well, 1 degree of freedom system with potential external force. And indeed, we have this quadrature here giving us a general solution. Okay, and also we have here a beautiful Liouville theorem, which applies well to a particular class of dynamical systems, or well, systems of ODEs, namely Hamiltonian systems, which you see here. So okay, so if we have well, canonical Hamiltonian system with n degrees of freedom, and we have n integrals of motion which are functionally independent and Poisson commute, then the system in question can be integrated by quadratures. So, okay, so we can get the general solution by quadratures. And now, a question which, well, arose a long time ago and proved to be quite trivial is how can one define integrability for systems of partial differential equations. Okay, so of course, one possibility is just to try to mimic what we had with integrability by quadratures, and requires that somehow we are able to produce a general solution for our system. Okay, so one example going in this direction is a well-known Burger's equation. So if we do the Kohl-Hopf transformation, we have the following well-known result. So if this guy V here is a general solution for the linear heat equation, then this U here is the general solution for the original nonlinear Burger's equation. But well, still this is not entirely satisfying, because well, there okay, there is of course a number of examples which behave like the Burger's equation, where we can write down a formula for the general solution, but the number of such examples is not too large. So the question is if we perhaps can somehow weaken the requirement of having of being able to write down a general solution, but still retain being able to let's say know enough about the solutions of our system or our equation. Okay, and so many people have applied considerable efforts trying to find a way forward, and the real progress in the matter was achieved somewhat a bit more than 60 years ago, when people discovered multi-soliton solutions for the Korteweg-de Vries equation, which you see as a slide, and which describes, among other things, shallow water waves. Okay, so more precisely, Kraskell and Zabusky around 1965 have, through numerical simulation at first, discovered solutions for KdV that describe two waves which collide elastically. Okay, and after some non-trivial interaction, part waves and keep their original shape. So, okay, so what we see here is what happens for the two-soliton solution. Okay, and then later on, it turned out that it is not just something that was observed numerically, that it is something much, much deeper. So later on, Green, Gardner, Kraskell, and Miura were able to find explicit exact formulae for multi-soliton solutions. Okay, these waves, which are separated at infinitely remote past and infinitely remote future, we've got the name of solitary waves or solitons. That's why the solution describing the interaction of multiple waves of this kind are called multi-soliton solutions. Okay, and okay, so and after Green, Gardner, Kraskell, and Miura, Peter Lex has uncovered the mechanism behind these nice results for the KdV. So he has shown basically that the KdV equation, although nonlinear itself, can be written as a compatibility condition for an overdetermined linear system. Okay, and what is important, it was later shown that the KDV is by no means an isolated example. There is actually a huge number of other integrable systems. Okay, so okay, so in this talk we'll be using the following definition of integrability, which is just a slight modification of the original idea of Lex. So we shall say that a nonlinear partial differential system, say capital S, is integrable, or more precisely, Lex integrable or integrable in the Lex sense, if this system is equivalent to a commutativity condition for a pair of linear partial differential operators L and M. Of course, in order that we get something meaningful out of this definition, we should require that these operators L and M are nice in a certain sense that I will not specify in much detail here. Okay. So in this talk, we shall all the time deal with integrability in the Lex sense. So I will just say that a system is integrable, meaning that it's integrable in the Lex sense. Okay, so if we have such a system, and okay, so we have a pair of operators L and M such that their commutativity is equivalent to our nonlinear system. Then, in this setting, L and M are called the Lex operators. These, in general, overdetermined linear system L psi equals 0, M psi equals 0 is called the Lex pair, and the commutativity condition LM commutator is equal to 0 is often called the Lex type representation for our system S. Okay, and of course, the nice thing about the Lex representation is that under certain technical assumptions, a system which is integrable in this Lex sense has infinite hierarchies of conservation laws and symmetries, and also infinitely many exact solutions can be constructed. Okay, so let's look a bit closer at this prototypic example of the KDV equation. But before that, let's introduce the following convention. So let ND indicate n independent variables, or n dimensions if you like. So 2D or 1 plus 1 stands for the case of independent variables and so on. Let me stress, however, for more for colleagues who are more inclined to physics, that in my talk, when I use this notation 2D, or especially 1 plus 1D, or 2 plus 1D, or 3 plus 1D, I do not imply the relativistic covariance of any kind. So let me stress you that in the theory of integrable systems, the notation like 1 plus 1D and so on, it doesn't really imply any relativistic covariance. So if we say that some system is 1 plus 1D or 2 plus 1D or whatever, we don't really mean that it is relativistically covariant. It may be, but this notation by no means implies that it is. Okay, so let's see how the KDV equation fits into this mold of Lex integrability. So indeed, if you consider the KDV equation 1, then it has a Lex type representation with L and M as shown in the slide. Okay, and well, let's note that the presence of the parameter lambda is actually quite important. okay, when obvious consequences that the Lex pair of psi equals 0, m psi equals 0 for this particular L and M can be actually slightly rewritten so that the first equation, L psi equals 0, is actually rewritten as a spectral problem. And in this connection, things like lambda are called are referred to as spectral parameters. Okay, proceeding with the KdV. Well, at this point, let me point out that, in fact, many highly important contributions to the theory of integrable systems were made by Japanese scientists. So one of these highly important contributions is the introduction of the so-called tau function by Ryogo Hirota. Okay, and in particular, in the case of KdV, the n-soliton solution for the KdV can be written in the fashion shown here, and this tau is this famous Hirota tau function for the case of KdV. Okay, and also without going into too much details, using the Lex pair for one can construct infinitely many conservation laws for the KdV. Okay, so in particular, one has an infinite series of non-trivial conservation laws for the KdV equation, which are shown here. And also, we have here an infinite hierarchy of commuting flows for the KdV equation, which in fact define symmetries of the original KdV and okay, commute pairwise and so form what is known as the KdV hierarchy. Okay, and now let me proceed closer to my results that will be discussed in the rest of the talk. We are still not there yet, but let me make an important point, which is that when we are given a certain nonlinear system and we look for a Lex-type representation for it, nothing prevents us from allowing that the Lex operators involve not just the variables present in the original system, but also some additional variables. And in fact, in some cases, this is quite necessary. So one such example where we need it is the so-called DKP or dispersionless KP equation. Okay, so it is known that for it we have a Lex pair with the operators L and M shown here. And please note that P that shows up in L and M is an additional variable not contained in the DKP equation itself. And moreover, the operators L and M contain derivatives with respect to P. So this is in a bit of a contrast with the KdV example that we have seen before. Let me remind you. Okay, so in the KdV case, we do have a parameter lambda in our Lex operators, but we have no derivatives with respect to lambda, while in the DKP case, we have also the derivatives with respect to this guy P. Okay, and for this reason, the Lux pairs of such a kind, which involve some additional variables, okay, more precisely, additional independent variables not present in the original system, and also involving the derivatives with such additional variables. So such Lex pairs are called non-isospectral, and okay, and in this setting, if we have just one such variable, which is typically the case, this additional variable, okay, in our case, which is with P, is referred to as a variable spectral parameter. Okay, so just to clarify, this Lex pair for DKP is quite well known. It's like, well, I guess like more or less, I think about 40 years old at this point. But interestingly enough, the idea itself of non-isospectral Lex pairs is even older, even though this terminology was not used at the time. So it turns out, at least to the best of my understanding, that the isomonodromic representations for the Penlever equations are, in fact, can be interpreted as non-isospectral Lex pairs. And such representations are known, I think, for more than 100 of years. So, in a sense, it's a very classical idea. Okay, now let's do a very brief panorama of what do integrable partial differential systems look like, depending on the number of independent variables. Okay, so if we have just two independent variables, so 2D or 1 plus 1D, in the notation I've introduced a bit earlier. So in this case, one has plenty of examples with the Lex operators having this form with A and B square matrices, which, okay, depend of course on the unknown functions or possibly vector functions for our system, and finitely many derivatives of this function, and also on the spectral parameter lambda. So actually, one can get a Lex type representation of this kind for the KdV equation, and another important example here is the nonlinear Schrödinger equation. So for this case, A and B are shown here, and just to allow you a moment of rest, let me just show you a the so-called Peregrine soliton for the nonlinear Schrödinger equation. So just you rest up a little bit. Okay, and now if we move on to the higher dimensions, things become somewhat more complicated. So if we look at integrable systems in 3D, that is 3 independent variables, then we have essentially 2 classes of examples. So one is such that operators L and M have this structure where A and B are differential operators in just one variable x. Okay, the best known and I guess one of the most important examples here is the AP system. Okay, so sigma is just a number which satisfies this. Okay, and the operators L and M are of this form. If we eliminate V from here, we would get the well-known KP equation. Okay, so and there is quite a number of examples of this general type. Okay, and here's the second large class of examples. So again, this is quite well known with classes, I guess okay. In this generality, I think it's known like for 30 years, although it's a little bit difficult to say who has formulated it in this generality. Okay, so in this second class of 3D integrable systems, what one has is the systems of this form, so quasi-linear homogeneous first order systems, and the Lex operators have the form star. Okay, so both U is of course the vector of dependent variables. Okay, F and G in this setting are called as Lex functions. Okay, and the operators XF and XG that we have in the Lex operator star are defined as follows. So for a function h of p and u, we define xh to be this quantity, which formally looks exactly like a Hamiltonian vector field in one degree of freedom, with the Hamiltonian being given just by the function h. Okay, so Lex operator star involve derivatives with respect to p. So again, p is an additional variable not present in the nonlinear system we are concerned with. Okay, so in other words, Lex operators star are non-isospectral, and p is the variable spectral parameter. And let me stress again that u does not depend on p. Okay, and of course, one example that fits this mold is this DKP system, which was already mentioned slightly earlier. And in fact, one has quite a huge number of such examples. So there are many choices of Lex functions, F and G, that allow you to get integrable systems, well, of this form. So it's not just one isolated example. Okay, but looking at things from the physics perspective, of course, one would be, I guess, especially interested in the case of 4 independent variables, or 4D. Well, and one reason, as we all know, is that general relativity of Einstein tells us that our space-time is 4-dimensional. So 4D partial differential systems, and in particular 4D integrable partial differential systems, are of quite some interest. Okay, and well, a long time it appears that unlike the cases of 2 and 3 independent variables, integrable 4D systems are quite scarce, and one doesn't have any effective construction for them. Okay, so from those that are known, the most important examples of integrable 4D systems are related with the concept of self-duality or anti-self-duality. So these most important examples are anti-self-dual vacuum Einstein equations and anti-self-dual Young-Mills equations, and okay, self-dual, of course, as well. And there is also a number of examples related to those, like the Przhanovsky equation, or general heavenly equation, or other heavenly equations by Plebansky. There is also a number of examples that do not appear to be directly related to self-duality. Okay, so the Naisky equation, Martinez-Alonso-Shabat equation, and some others. But still, let me stress, there is not too many of them. And interestingly, the overwhelming majority of the previously known integrable 4D systems can be written in what is sometimes called the dispersionless form, which means that they can be written as quasi-linear homogeneous first-order partial differential systems. Just to illustrate this statement, let me show you how the Sergyeyev-Mills equations can be written in the dispersionless form. So, first of all, it can be shown that these equations, in fact, can be reduced to a single equation for the Young matrix J. Okay, assuming that the gauge group is a matrix-Lie group, of course. Okay, and this equation is rather easily rewritten in dispersionless form by introducing an additional, let's say matrix potential W. Okay, so this is the dispersionless form for the equations on the study, and just for the sake of completeness, here is the Lex pair for these equations. Okay, so if we try to sum up, so for a long time, it appeared that what we have is the following situation, that in 3D, we do have some effective constructions for integrable systems. Okay, so one is the central extension. Okay, I will not go into details here, but this is the one we have seen in, okay, the KP equation or the KP system is one of examples that can be obtained within this central extension framework. Okay, so another powerful construction is the one using Hamiltonian vector fields, which, okay, we have looked at that before. And of course, there are some, let's say, sporadic examples that do not fit into these two general constructions. Okay, and in 4D, for a long time, it appeared that all one has are some basic sporadic examples. So it appears that there is no effective construction allowing one to produce some classes of 4D integrable systems. But actually, the main method for you to take home from today's talk is that there does exist such an effective construction. So, in fact, in 4D, in addition to these previously known sporadic examples, there is an effective construction involving contact vector fields that allows one to produce infinitely many new 3+1 dimensional integrable systems. Okay, so now let me describe this construction. So we assume that the Lex operators have the form shown in the slide. Okay, so F and G are called again Lex functions, just as in the 3D case. Okay, so U is the vector of unknown functions for the associated nonlinear system. So it depends on 4 independent variables, which we denote by X, Y, Z, and T. P is the variable spectral parameter, and this guy Xh, which is used in the definition of the Lex operators, has the following form. So formally, it looks exactly like the 3-dimensional contact vector field with respect to the contact form z plus pdx and with the contact Hamiltonian small h. Okay, so and just a small remark that the associated Lex pair can be rewritten in this form. Okay, so and again, let me reiterate that P is variable spectral parameter, and the vector function u does not depend on it. Okay, so the key claim here is that this construction produces infinitely many new 4D integrable systems. In particular, we have the following theorem that for all natural m and n and all pairs f and g given by these two sets of formulae, so the Roman 1 and the Roman 2, the Lex pairs of the kind shown in the previous slide, namely these ones, yield 4D integrable systems. And moreover, what is important is that these integrable systems are reasonable in a sense that they can be transformed into Cauchy-Kovalevsky form. So at the very least, this indicates that these systems are not overdetermined. And this is actually quite an important point because, well, it is not too difficult to produce examples of integrable systems which while do involve 4 independent variables, are so highly overdetermined that they effectively behave as systems with a lower number of independent variables. But for these two infinite classes of functions f and g and these Lex pairs shown here, it is not the case. So in other words, once again, these two classes of pairs f and g use through the Lex pairs of this form infinitely many integrable systems which are say genuinely 4-dimensional in that they are not overdetermined. Okay, let me show you a simple example of this construction. Let f and g be of this form. So, okay, so I've slightly changed the notation for this example. Okay, so here is how it relates to the notation from the theorem. It's example from the first class from the above theorem. Okay, if we spell out explicit Lex pair for this choice of functions f and g, then the Lex pair we are concerned with, this one can be spelled out like that. Okay, and if we write down the compatibility condition for this Lex pair, it turns out that gives rise to the nonlinear system 3. Okay, and what is interesting about this system is that up to some simple rescalings, this system is actually an integrable generalization to the case of 4 independent variables for the DKP equation which we have seen before. Okay, so now let's look a bit closer at the class of the Lex pairs we are dealing with. Let me remind for your convenience that the operator xh, which is used in the definition of the Lex operators, is shown here. So it formally looks like a 3D contact vector field with respect to the contact form dz plus pdx. Okay, okay, of course, when we write down the conditions that the commutator of L and M for this particular choice of L and M, okay, so the conditions that the commutator of such L and M vanishes actually is equivalent to the following more easier to deal with condition, namely this one here. Okay, and the bracket involved is known, or at least sometimes referred to as the contact bracket. Okay, so that's what we have, and okay, and of course, if this commutativity condition LM commutator equal to 0 holds, then it implies the compatibility of the associated Lex pair. Okay. Well, also let me note that actually for the lecture we are considering, we have the following natural interpretation of the function chi. So the idea is this: if we fix a certain smooth solution for our associated nonlinear system, then actually upon this done, the function chi can be interpreted as a joint integral of motion for the following pair of contact dynamical systems. Okay, so we have at least a bit of understanding what is the meaning of the function chi in the Lex pair. Okay, so now, all right, and let me point out another important fact. So again, consider the Lex pair of the class we are interested in, this one. So if we impose a reduction and assume that both U and chi are not depending on Z, then the Lex pair star boils down to a Lex pair producing integrable systems in 3 rather than 4 independent variables. Namely, upon this reduction, the Lex pair star boils down to this one, and this is a this is the kind of Lex pairs that we have already seen before. The ones that have these operators formally looking like Hamiltonian rather than contact vector fields. Okay, so that much for the reduction of systems from our class. Okay, and let's explore a bit more closely the first of the 2 infinite classes of pairs of Lex functions that give rise to 4D integrable systems. So the class in question is such that f and g are monic polynomials in T. Well, f is a completely generic monic polynomial. G is almost generic. The only coefficient that has a special form is the next to highest order coefficient, this one. Okay, and well, if we write down the associated Lex pair and check its compatibility condition, it turns out that we end up with the following system. Okay, it is fairly complicated, I admit. Okay, so first of all, it's quadratic. And actually, it can be shown that this is an evolution system in disguise, in the sense that when we consider for a moment this system as an algebraic system, we can solve it with respect to z derivatives of all variables ui and vj. So, as I said, it's actually an evolution system in disguise. Okay, and now let's also take a quick look at the class of the second class of Lex functions from the main theorem. So these are rational functions of this form. So again, m and m are arbitrary natural numbers. Okay. So, well, when we write down the associated Lex pair, okay, we would see that the associated nonlinear system is this one, okay, fairly huge and complicated. But still, again, it is quite reasonable, and in particular, it can be brought into Cauchy-Kovalevsky form. For example, if we do this simple change of independent variables, namely replace t by this new variable capital T and keep all other variables intact. All right, so okay, so again, we have this key theorem, which gives us two infinite classes of new 4D integrable systems. Okay, and a natural question comes up whether the Lex pairs of this form, I'm showing you using the cursor, whether one could get some further examples going beyond this theorem, and it turns out that this indeed can be done. In particular, if, for example, we make this choice for functions f and g, so now f and g are no longer rational but algebraic in P, then if we consider the associated Lex pair and write down the compatibility condition, we get, okay, a rather large and complicated system of this form. But what is interesting about this huge system is, in fact, that this is the first known example of a 4D integrable system such that its Lex pair is non-isospectral, and the Lex operators are algebraic rather than, say, rational in the parameter P. Okay, so this particular system is explored in more detail in this reference. Okay. Also, let me touch upon some open questions related to the construction of the Lex pairs star. So, one such question is whether we can go even a bit further and have not just Lex operators which are algebraic in P, but also say Lex operators which would be transcendental in P. Okay, and to other natural questions that come up, okay, it would be interesting to fix the number capital N, that is the dimension of the vector of unknown functions in the associated nonlinear system, and attempt to classify all pairs of Lex functions f and g such that the associated Lex pairs are produce integrable nonlinear 4D systems. Another related question is whether one could find any pairs f and g such that the Lex pairs star would produce integrable 4D systems with less than 4 dependent variables. Okay, and now I think I can summarize. So, okay, so the key point of this talk is that there is far more integrable systems in 4 independent variables than it appeared before. And in particular, there is infinitely many new 4D integrable systems with the Lex pairs of this form. Okay, where xh is once again reminded here. Okay, and a nice thing about this construction is, okay, so for one, as I said, that this construction produces infinitely many integrable 4D systems with, well, like functions fng that are either polynomial or rational. And also, this same construction allowed us to produce the first, at least to the very best of my knowledge, the first known example of a 4D integrable system that the known as a spectral Lex pair such that its Lex operators are algebraic rather than rational in the spectral parameter P. Okay, so the main reference for this general construction is this paper of mine. So, and at this point, let me thank you very much for your attention. Domo arigato gozaimasu. Thank you very much.
Thank you very much for a very interesting talk.